So the next presentation is based out of the University of Vermont. I mentioned it earlier. It is a group, a road salt reduction task force. It was actually established by the physical plant and the facilities, again, based on infrastructure challenges that they were observing costs, exorbitant costs for having to make repairs due to salt damages. And they brought together a team from across campus from multiple departments, faculty, students, staff, representing custodial, facilities, grounds, the people who are looking at the buildings and managing the infrastructure, and again, people who are monitoring water. So the story that will be told here in the next 38 minutes, Lynn Wood, who is the physical plant Davis and Trinity zone manager, herded us cats from this team to have people share their individual perspectives and stories of why it matters to them and the projects and the actions that they are working to take to be able to manage salt and reduce salt on campus.
Welcome to our presentation, the University of Vermont, the Salt Mitigation Task Force 2021. This is a story about sustainability. My favorite definition of sustainability is meeting the needs of the present without compromising the ability of future generations to meet their own needs. Sustainability is typically noted as the intersection or pillars of three sectors: environmental, economic, and social. In our case, the environmental impact is related to a habitat. Economic impacts involve the repair replacement dollars associated with the damage from salt usage, and the social aspect is educating our community about salt mitigation, awareness of salt application processes, and of course, our people, and ensuring the work environment and practices keep them safe. The salt mitigation team recognizes that the campus will need to use salt in the future to maintain a safe campus, but perhaps with better planning and engineered solutions, we can lessen the impact to the environment and our facilities and reduce our usage across campus while still maintaining the necessary safe passage of our community members. A little background of how we came together. We call ourselves the Salt Mitigation Task Force. Our team has representation from facilities, the School of Engineering, and the School of Natural Resources. The agenda varies between sampling, costs, data, and new products we are trying. Like many universities and organizations, the pandemic changed the mode of communication, and we found that Microsoft Teams was the most efficient platform for communicating. Money is the catalyst that brought us together. We were spending a lot of money on facility repairs, both above and below ground. One of our initial meetings, we had pulled together some rough numbers of past, current, and future projects. These projects were having premature failures, so we were having to redirect funds in lieu of other projects. This, coupled with pictures you will see throughout the presentation, really painted a picture for the need to look at a more comprehensive salt mitigation strategy. As you can see, we were spending close to $2 million on repairs related to salt over a 5-year period.
We know from the New Hampshire Department of Transportation that salt has been used on roads to lower the freezing point of water and therefore to minimize the formation of ice on roads and other surfaces since the early 1940s. The challenge is that when we put salt, which is sodium chloride, on the roads, it can run off and can have impacts on the environment. For instance, if sodium chloride gets into surface water bodies, it can actually reduce the reproduction ability of fish or other aquatic life, and it can also kill them at certain higher levels. We also know that chloride entering lakes can affect natural lake processes. It's going to sit on the bottom because that salt is more dense than the fresh waters, and it can inhibit normal cycling or mixing of the lake. Here in the Lake Champlain Basin, we know from research from the Osable River Association, from Brendan Wiltsey, that Mirror Lake in Lake Placid has been salted because of that urban community. The salt actually runs down into the bottom of the lake, and it forms a salt wedge at the bottom, which is rich in chloride, low in oxygen, and that means the fish stay up above. In a normal spring situation, mixing would happen from top to bottom. When the ice is going out, there would be enrichment of oxygen again to the bottom waters. However, what Brendan has found is that because of the salt wedge at the bottom, full mixing of the lake doesn't happen, and that means that low oxygen levels stay at the bottom, and the fish therefore stay higher up. This is okay until you get to summer, when the top waters start to get very warm, and warm waters hold less oxygen than cold waters. And as the summer goes on, the fish are squeezed more and more into a narrow band of the lake, again as a result of the salt having been put there in the winter. Other impacts of salt on the environment include running off into roadside areas and killing vegetation, as can be seen here. Salt also can move its way into the soil. It can change the microbes that are in the soil, which can change how permeable or how much water that soil is able to hold. And it also can cause the release of any toxic metals that might be in the soil, possibly as a result of cars or other inputs from the roadways. Salt also can get into groundwater, and a number of people are using groundwater as drinking water. In this area, we know that there have been contaminated wells, and in this case, sodium chloride is our road salt, and so the sodium levels can be impactful to people who have high blood pressure or other dietary restrictions or health concerns. And so having groundwater contamination is a challenge. So in the Lake Champlain watershed, the area that drains the Lake Champlain, we know that chloride has been increasing at least for the last decade. On this graph from the Lake Champlain Basin Program, we see chloride on the vertical axis, time on the horizontal axis, and you can see that from about 2011 or so, we've seen increasing concentrations of chloride in the lake. This is a result of all of the tributaries entering Lake Champlain having increasing chloride in that time period. So all of the rectangles you see alongside Lake Champlain in the graph on the right are tributaries, the main tributaries to Lake Champlain. If you look towards the right-hand side of each of those rectangles, the line tends to be going upwards to the right. This is an indication that chloride has been increasing from about 2010 to about 2020. In the monitored time periods. So the tributaries are influencing what's happening in the lake. We know that Vermont has 5 streams that are listed as impaired for chloride, and that means that those streams need to have what's called a total maximum daily load, or a pollution diet, to determine how we will have less chloride entering those water bodies to protect them and the aquatic life within them, as well as human connections through drinking water. Most of these streams, or all of these streams, are within the Burlington area, and 2 of the streams are draining parts of the UVM campus. Anglesey Brook drains the southern end of campus, which is shown in the orange rectangle on this map, and Centennial Brook Watershed drains the eastern part of the campus. But I want to point out that campus is not the only contributor to these streams, and therefore not the only contributor to the chloride concentrations being observed. For instance, in Centennial Brook Watershed, you can see I-89 is running through that watershed. We have a main thoroughfare down into the city of Burlington. We also have the edge of the airport as in the headwaters of that stream. So UVM is one of the contributors, but not the only contributor.
I'm going to talk to you about the financial impact of salt application as it relates to our buildings. As you saw from the previous slides, the dollar figures associated with some of the costs for implementing projects. Now I'll show you on the other side of things the physical pictures associated with what those costs look like. The University of Vermont is a large campus located in Burlington, Vermont. Prior to COVID, we had a budget of about $16 million for deferred maintenance. But with all of the budget reductions during the pandemic, we are currently budgeted at about $6 million in deferred maintenance, which is not a lot when there are so many buildings and funds shared for things like roof replacements, mechanical systems, electrical upgrades, and life safety upgrades. It really hurts to use these limited funds to make repairs that are a result of salt damage. We would prefer to build a project that will have a 15 to 30 year life. The above ground building items that tend to be the most costly are the entrances, the storefronts, stairs, metal doors and frames, and masonry. The pictures really tell the story of the damage we see from salt. This area is the entrance to our new central dining facility turned over to us in 2017. We are seeing corrosion on steel beams, mullions, and just about everywhere the carpet abuts the metal. Note how quickly the damage begins to happen. But it is not just the metals that we see the damage. Many locations across campus also have failing mortar and stone on projects less than 10 years old. We have a lot of historic buildings across campus as well. This is our Williams Hall, which I show the larger photos for reference, but then narrow in to the granite pillars that are at the entrance. Notice the disintegration that is happening to the pillars due to the salting of the entryways. Our hope is that we can find sealants or have maintenance strategies to eliminate further degradation. Our doors are another obvious area of failures due to salt, and you will notice it is only the bottom 12 inches of the frames and doors that we're seeing this rust and corrosion, again indicating this is a salt problem. This is a picture of our manhole doors recently replaced. These are newly installed, but you can see the rusted areas of the old doors. Our latest approach is to coat the bottom 12 inches of the doors and frames with a Rust-Oleum product that is a primer that is epoxy based. Our hope is that this protects the metals for a longer life. For above ground issues, I would say our stairs see the most damage. The university's original design of stairs included a metal nosing, but due to freeze-thaw cycles and expansion-contraction of metals, coupled with salt usage, the failures of these nosings are significant, and to date, we have not found an easy repair. Our new stairs have gone back to previous designs without the nosings, but salt still finds its way into the concrete and reacts with the rebar. We are planning to include maintenance for sidewalk and stair sealant. The previous slide included the house stairs before construction. Now completed, these stairs incorporated our new design, eliminating nosings. We are hopeful that designs mitigating salt damage, better products, and more comprehensive maintenance techniques, coupled with technology changes with more innovative approaches, are on the horizon.
Hello, my name is Kevin Sweeney and I'm a project coordinator with the university. I work a lot on the underground utility systems, and in particular I want to talk about our utility vault and some of the salt penetration issues we're seeing with those vaults. But just for a little bit of background, we have a central utility plant that serves over 80 buildings with steam and 20 buildings with chilled water for heating and air conditioning systems. We have over 5 miles of underground steam piping and over 2 miles of chilled water piping throughout campus, and 42 utility vaults which house valve work, trap assemblies, and other equipment that maintain that distribution. Over the years, we've seen more significant salt penetration issues into our utility vaults. This is a photo of utility vault MH4, which supplies steam and chilled water to Central Campus. This has salt penetration through the roof seam as well as the manway, and has accumulation of salt on this anywhere from the steam jacketing to the carbon steel piping, the floor, and some of the electrical components inside the vault. This has some challenges with construction as it's located in a major roadway, and would need to have the roof slabs and replaced and re-waterproofed. Last year, we noticed concrete spalling and cracking in MHS5, which is a steam vault that serves steam to one of our major dormitories here on campus. After we took that photo, we noticed concrete falling down into the structure and worked with some of our local engineering consultants to come up with temporary shoring until we could make repairs to the vault. We ended up increasing the elevation and bringing the vent structure, the vents above grade so that runoff would not be an issue into the vault, and then waterproofing the vault itself, all for a cost of over $167,000. We are currently under construction on our MHN2 utility vault repair project. This vault had significant spalling of concrete in the roof structure, which was located underneath the manway and a sidewalk above. After we noticed the spalling concrete, we took temporary supports and shoring and used that to support the roof, to buy us time to seek engineering consultants and get project specifications and drawings completed for the repair. During the engineering evaluation, we found additional vault wall failures and floor delamination of the concrete itself, and went out for bid and started the repair, and had additional discoveries of corroded sleeves, which you could see in the top right, which needed to be replaced. So we made additional modifications and put in new sleeves and seals for the project. And we are seeing costs of roughly $565,000 for this project. The utility vault MHN2 repair project had a number of different challenges associated with it, from pedestrian access and minimizing blockading walkways to emergency vehicle response access ways and conducting modeling for turning radiuses, to just logistical challenges with removed access to loading docks, trash removal, and other delivery points on campus. Another challenge was the working with live steam. This is one of 42 utility vaults on campus, and is really the hub between North and South Campus. So it's one of the most critical vaults on campus. Isolating the utilities prior to the project would be detrimental to the HVAC and heating systems, both on North and South Campus. And we really needed to keep this live while we were doing the construction. So access to valve work, maintaining thrust block anchors, and moving of equipment was critical to maintaining the system's operation.
The UVM Custodial Services team consists of 203 full-time employees. We are a very diversified staff with over 10 years experience on average, and an average age of over 50 years old. We have 2 Kubotas, a Bobcat with a Salter, and 14 snowblowers to service our larger areas. We're on call 24 hours a day during the winter months for a total of 20 weeks. We have no contractors. We service 116 buildings and 373 access egress sites to include porches and patios. Safety drives our response 24/7. Like grounds, we don't have a bare pavement policy. After a major winter event, our goal is to complete the clearing of all access egress points within 72 hours. Proactively, we apply a de-icer, a potassium formate base. As a pretreatment, we use pump-up sprayers before the storms. This creates a barrier so that ice will not bond to surfaces. It is also meant for light accumulations of snow otherwise. We salt during snow events and during icing events. This is meant for accumulating amounts. For equipment and supplies, we have 1 and 2 stage snow blowers, salt spreaders, handheld, walk behind and mechanical, pump up sprayers, shovels, ice scrapers, handheld spreaders, and picks. For chemicals, we have de-icer, a potassium formate base, as well as salt, which is based in calcium, potassium, magnesium, and sodium. Our custodial organization has annual equipment and supply budgeting of about $70,000 a year. We spend this money on salt, which has averaged us about $50,000 a year over 5 years, de-icer, which we've used for a couple of years and averages us $14,000 a year, and equipment, for which we are budgeted $6,000 a year. Custodial has a variety of equipment for the removal of ice and snow. We have snow blowers, ergonomic shovels of various kinds, broadcast spreaders for salt, handheld spreaders for salt, and pump-up sprayers for the application of pre-treatments to prevent ice buildup. The equipment comes in various shapes and sizes. The idea is we want to make it as safe and easy as possible for our people to remove ice and snow from the facility. The pump-up sprayer for the application of our pre-treat is critical. We began using this a couple of years ago. It's battery operated, it's lightweight, and can be used walking either forwards or backwards. The important thing is you maintain situational awareness. Here we see it in practice. Simply provide a nice, even coating. The concept is to provide a barrier that prevents ice from forming on the surface that you're applying it to. The salt spreaders, a handheld, is adjustable. Makes it much easier to control the volumes of salt that you're putting down, so you ensure that you're not piling it up. And it's really good around the doorways so that you don't get salt buildup and corrosion.
The University of Vermont is in the heart of Burlington, Vermont. As you can see by the slide, we get almost 7 feet of snow here on average. Here you see a picture of the damage from the Great Ice Storm of 1998. This was well before my time at UVM, but one of our staff members, who is in his 41st year with UVM Grounds, talks about the cleanup that took weeks. Let's hope we don't see another storm like this for a long time. We include this slide because icing events have become more prevalent in recent years and we believe has driven our increases in salt use. At UVM Grounds, we use a combination of in-house staff and contracted help. The grounds team on-call schedule goes from November to April. We currently rely on 4 contractors for snow and/or ice management to remove snow from designated campus areas and satellite areas. Our campus is fairly large, about 600 acres not including satellite areas, therefore necessary to hire outside help. As the slide says, safety is our top priority. We don't have a bare pavement policy per se, but have a goal of clearing our hard surfaces to mostly bare in a reasonable amount of time. As I said before, ice events are occurring more frequently in recent years, and this is a challenge for us because ice creates more risk of slip and falls. We take a proactive approach to fighting storms. We watch the weather forecast carefully and schedule our crews to come in off hours when necessary. Sometimes these storms coincide with athletic events, which raises our challenge to keep the campus safe, especially given the fact that many of our spectators to sporting events are elderly. We also have to react quickly, such as when we have a warm spell that melts snow onto the road surface only to refreeze in the middle of the night. When storms are forecasted, we apply anti-icing liquid with magnesium chloride to our hard surfaces. The anti-icing liquid helps to break the molecular bond between the ice and the paved surface, making clearing off of it more efficient. Also, less salt is required. Before we began anti-icing, we would have to rely on rock salt to melt the ice. We are confident that anti-icing has reduced the growth rate of our salt use. In addition to ProMelt, we apply a bagged magnesium chloride product to our parking garage instead of rock salt because it is less corrosive to rebar and other steel structural members of the garage. To combat and reverse the trend of increased salt usage, we have invested in technologies that will help us to reduce and optimize our salt usage. This year, we purchased equipment from Hilltip and took advantage of a grant that is funded by a UVM student fee that the students put in place. The funding allows for student participation to study the equipment and report recommendations. This year, we purchased a Hilltip truck-mounted combination liquid and solid spreader. It has the capability of spreading rock salt and any liquid de-icer. We also have purchased 2 Hilltip liquid spreaders for our sidewalk machines. The Hilltip equipment has geo-tracking and the capability to predetermine the flow that is applied to a specific area based on the settings we choose. This helps take the guesswork and personal preferences of the operator out of the equation. However, the equipment operator has the option to blast the area with extra product if it is needed. We are excited to begin using these products because we believe that it will help us to fine-tune our operations to a degree which we have not been able to do in the past, and it will pay dividends in terms of salt reduction, environmental benefits, and safety. Our annual salt use has trended upwards, we believe due to the increase in icing events, and costs us about $200,000 per year. It is one of the reasons, in addition to a desire to reduce impacts on the environment, that we are taking a proactive approach to salt reduction strategies. We have 3 salt sheds. Each shed holds 300 tons, which when filled allows us to have almost half a season's supply on hand. We built the extra capacity to protect us from salt shortages, which have been a problem in the past years. We have 2 4,500-gallon tanks that we use to store a liquid magnesium chloride product, which is called ProMelt Ultra 2000 Inhibited, that our staff mixes into the rock salt. As the name suggests, it has a rust inhibitor added to the product. This is the same product that we use for anti-icing, with the exception that the liquid that we mix with the salt has a dye added to it. We added this graphic here to give you an idea of what a ton of salt looks like. It is about a cubic yard in size. Here's a quick video of our truck-mounted Hilltip combination liquid and solid spreader. As you can see, there is a hand sprayer that we can use for entranceways and stairs. Also, the nozzles can be adjusted for conditions such as snow depth. In addition to the capability of the unit to spread either liquid or solid product, it can pre-wet the salt as it flows from the spreader.
In the early 1940s, when salt was first used on New Hampshire roadways, about 5,000 tons of salt were used per year in the U.S. If you fast forward to 2015, about 20 million metric tons of salt were used in the U.S. So how much is that? First off, there's 2,200 pounds of salt in a metric ton, and if we say each salt truck can hold about 10 tons of salt, that forms a traffic jam of salt trucks from Burlington, Vermont to Seattle, Washington, back to Burlington, Vermont, all the way to Glacier National Park. That's a lot of salt.
Stormwater treatment pond monitoring was necessary for us to quantify the impact of our salt reduction efforts. Our goal was to develop a water quality monitoring program for stormwater treatment ponds in the UVM watershed. This student-led monitoring program allows us to develop a baseline data set for water quality parameters in the UVM campus stormwater treatment ponds before the application of de-icing agents on campus. The rationale for this part of the project is related to the fact that there is currently limited data on water quality in the UVM stormwater treatment ponds. Extremely high levels of conductivity and chloride have been measured in nearby Centennial Brook, which accepts the portion of water that drains from the retention ponds on campus and then drains to Lake Champlain. We believe that by collecting baseline data on chloride, conductivity, and other basic water quality parameters, we will be able to assess the long-term impacts of salt reduction efforts on campus. A watershed map of UVM campus can be seen here. Our stormwater treatment pond monitoring included 5 of the 7 stormwater treatment facilities fed by UVM campus. Sites examined include Main Street East Stormwater Treatment Facility, East Campus Stormwater Treatment Facility, and North Campus Stormwater Treatment Facility, which feed into Centennial Brook, represented by the red line on the map. Other sites include Southwest Stormwater Treatment Facility No. 1 and Southwest Stormwater Treatment Facility No. 2, which feed into Anglesby Brook, which is located slightly south of these treatment facilities. Weekly monitoring of conductivity, dissolved oxygen, pH, and turbidity started on June 9, 2021 and continues to present date. Most sampling occurred within 2 days of a precipitation event. The impact of precipitation events in stormwater ponds is shown by this comparison of Main Street East Stormwater Treatment Facility's water level. The latter photo was taken after 2.64 inches of rain fell in a 48-hour period. Samples were collected near the stormwater pond outflows in 500 milliliter HDPE bottles, first by hand from shore and then later using a 12-foot sampling arm. Samples were stored on ice and analyzed within 24 hours in the Environmental Engineering Teaching Lab at UVM. Water level data was collected beginning July 20th, 2021 using a Topcom self-leveling laser level and receiver. We explored the use of staff gauges to measure water level, but couldn't find a consistent method of anchoring or attaching the gauge at outflows due to differences in pond outflow structures, substrate, shore composition, and depth. Various stormwater treatment facility outflows are shown here, including trash rack outflows and concrete structure outflows. Results of the conductivity analysis for a single stormwater treatment facility can be seen here. This graph depicts conductivity as it relates to rainfall. Rainfall is measured in inches and is represented by the blue bars, with the rainfall scale to the left of the graph. Conductivity is measured in microsiemens per centimeter, represented by the orange line, with the scale to the right of the graph. Weekly sample collection dates can be found on the bottom axis of the graph. Trends for this graph show higher conductivity during lack of rainfall, followed by decline in conductivity values after rain events. This is likely caused by rainfall events diluting the present salinity concentration in the stormwater ponds. We expect these conductivity values to increase once the application of de-icing agents begins on UVM campus. This is our baseline data. The period for collection of baseline data is June 2021 until the first application of de-icing agents on UVM campus this fall or winter. We are continuously building on this data set. Shown here is all our data for this baseline period in the 5 stormwater ponds that have been monitored so far. Moving forward, we anticipate deploying high-frequency data loggers for collection of water depth, temperature, and conductivity. This will allow for continuous monitoring through the winter when accessing the ponds for sampling will not be possible due to ice. We plan on continuing weekly site visits to check on the deployed data loggers and collect samples for dissolved oxygen, pH, conductivity, and turbidity, so long as we can remain safe on the ice. Standard methods for our laboratory procedures are cited here. Following this slide, we will be watching some videos of the sampling process and lab analysis.
Here you can see a water sample being taken from East Campus Stormwater Treatment Facility. The duckweed is brushed away from the surface to ensure it does not compromise our dissolved oxygen measurements. Here you can see Robbie taking samples from North Campus Stormwater Treatment Facility. The sampling arm bottle is rinsed 3 times with pond water before a sample is taken to prevent contamination. This is what our typical sampling day is like. This is me analyzing the dissolved oxygen of our stormwater samples in the Environmental Engineering Teaching Lab at the University of Vermont. Here's Robbie calibrating our turbidity meter. Samples were typically calibrated using a 10 NTU calibration standard.
We have reached the conclusion of our presentation. We started meeting as a team January 5th of 2021, and we really feel this is the beginning of an adventure. We have a tremendous opportunity to make changes that impact our campus and the environment in a positive way. We are fortunate to have multidisciplines able to tackle these challenges from many different angles, in essence, performing research with the campus being our laboratory. We may be a newly formed group, just 10 months, but individually we bring a lot of experience to the table, and collectively our team approach allows us the ability of experimentation. As we implement a change, we can then evaluate the results through our sampling. We could even conduct 3 different experiments based on the 3 different areas on campus that feed the 3 stormwater ponds. Variance in salt amounts or a different product, coupled with engineered solutions, all possibilities in our laboratory. For the very long term, we would hope that our approach gains traction and others will find alternative ways of melting snow and ice on roads and entrances, and also find other methods to mitigate damage to facilities and grounds. We have more goals, and we can share our executive summary, vision, and mission through a link we will provide at the end of the presentation. It's been a summer where a lot of data has been collected. That is our baseline. But I know our student researchers are anxious to see what happens next after that first snowfall or ice event that forces the campus to begin the salt application on our roads, walkways, stairs, and entrances. That will be a milestone day for us. Some other up-and-coming events include alternative sensors to collect data. We have a large custodial staff, and Chris and Caleb are creating a training video. Another emerging plan is to have a survey deployed looking for feedback from other campus environments to share their stories and practices. And we have a new piece of equipment arriving any day that will be programmed with geo-tracking to calculate and monitor our salt application based on weather data. Exciting stuff. I want to conclude with a special thanks to the Sustainable Campus Fund. Each semester, students contribute $10 to replenish the funds, which total about $230,000 annually. This fund was originated and established by students in an effort to further a culture of sustainability, innovation, and research on campus. Students, faculty, and staff can submit a proposal to the SCF 2 separate times a year and request funding for pilot programs. Kudos to Courtney, a member of our team, who put together a thorough proposal that was selected as a new pilot program. Many proposals are evaluated by SRIAC, Socially Responsible Investing Advisory Council, and selected based on relevance. As a campus with a large research community, it is extremely important to have students involved in projects like these, because they will be the generation that makes impactful change for the future. Thank you for your time today. Credits with contact information will follow this part of the presentation. Feel free to reach out to us.